Hello everybody and welcome. In this video I'm going to show you how to set up an ESD workstation in your house or apartment so that you can handle your 18F4550 or other ESD sensitive chip without doing electrostatic discharge damage to it. Caution: some of the footage in this video involves working with mains electricity, in other words the outlets in your house or apartment. Mains electricity is 120 volts alternating current. In the United States it could be different depending on what country you live in. But in any case, in any country, mains electricity is enough that it can kill you. Use common sense, double check yourself, stay sharp, and do not continue if you have any doubts or do not fully understand any part of this video. Going forward, you accept 100% of the responsibility for any damage to life, limb, or property. Continue at your own risk. So before we get into some of the practical aspects of setting up an ESD workstation, let's do a quick crash course in ESD theory. Your body can hold thousands of volts of charge. For example, you might be able to recall times that you took warm clothes out of a dryer and heard sort of a crackling sound, or you may have purposefully scrubbed your feet on a fuzzy carpet and then touched somebody else to shock them. The thing that we need to consider is that static electricity discharge that's even far less than can be felt or heard by people can still be more than sufficient to damage ESD-sensitive electronics parts. Something else that we should also be aware of is the difference between TTL chips and CMOS chips. TTL is short for transistor to transistor logic. When ICs were first developed, TTL chips were standard, but as time's gone on, we've demanded more and more from our ICs. They've had to get smaller and smaller, and they've had to have more and more transistors on them. And this has resulted in more and more crowded chips, which inherently are more static sensitive. Particularly today, most chips are CMOS chips. That's short for complementary metal oxide semiconductor. So pretty much all modern ICs, including almost all microcontrollers such as the 18F4550, are CMOS chips and therefore ESD sensitive. I won't get into ESD theory anymore at this point. I'd like to get into the practical aspects of it next, but if you're interested, there's plenty of resources on the internet. For example, if we type in ESD, we'll get the Wikipedia page on electrostatic discharge, and there's this nice section here on damage prevention in electronics. Similarly, if we type in TTO and we follow a few links, we'll get to the Wikipedia page on TTL chips, or we can type in CMOS and we'll quickly get to the Wikipedia page on CMOS chips. But rather than get bogged down in theory, let's go on to the practical aspects. So here's the idea. We're going to have the 18F4550 or other ESD sensitive chip grounded at all times. So if ground's down here, what goes in between? Well, of course, we're handling the 18F4550, and then we have an ESD mat, and then we have to connect that mat to ground. So, of course, our hand holds the 18F4550, so then we're going to use a wrist strap and wrist strap cord to connect ourselves to an ESD mat, and then we're going to use a ground cord to connect the mat to ground. So, of course, it's essential then that we have an ESD mat kit to set up our ESD workstation. Personally, I recommend getting one from esdmat.com. This part number specifically, we'll take a look at that in a moment. Also, you don't want to just toss your ESD sensitive chips in a drawer. They can touch the drawer itself, other parts. That's not good. That can also do ESD damage. So what you want to do is you want to get yourself some ESD bags to store your 18F4550s. And here's a recommended part number at Electronics Express. Also, once you get your nice new ESD mat, you want to get some ESD mat cleaner with that, because you really don't want to use general household cleaners with your ESD mat. They leave a residue which can reduce the mat's ability to dissipate charge. And in the case of severe household cleaners, cleaners with bleach in them, that kind of thing, they can corrode the mat. Also, if you use hand lotion often, like especially in the winter if your hands get dry, you want to get some ESD hand lotion, which is nice because it does not leave a gummy residue like regular off-the-shelf hand lotion does. So now let's take a look at www.esdmat.com. And these nice work surface mat kits here are probably what you want to get. You can get all the parts individually, but I recommend a kit. Specifically, I recommend these high temperature mat kits. And these have a nice thick rubber layer on top. So they're kind of resistant to scratches and abrasions and so on, so you can do assembly on them without worrying about damaging them much. Also, these mats will withstand soldering iron contacts. This is critical because at some point, no matter how careful you are, you're going to end up touching a hot soldering iron to the tip of your mat. Make sure you get a mat that can withstand that. I definitely recommend getting the biggest mat you possibly can because you're going to use all the room that you have. You always end up filling it up inevitably. So I'd recommend the 3 foot by 4 foot mat. Okay, so the first thing you're going to want to do when you get your ESD mat kit in the mail is unroll the mat on your desktop and then take a look at the other parts that come with your kit. And here's what you're going to find. You're going to find a wrist strap cord, and a ground strap. Now the wrist strap has two ends. This end here, the banana jack end, goes into one end of the ground cord. The other end simply goes into the wrist strap. So then once we've made those connections, and you'll notice there's metal here to make it conductive. So once we've made those connections and we put our wrist strap on, at that point, if this is grounded, then we're grounded. So that brings us to the other end of the ground cord, which is this loop. So we're going to have to ground this either through the ground of our wall outlet, or we'll have to take it to an actual piece of metal such as a pipe or a radiator that's going into the ground. I'll get to that in a moment, but first let's do some safety checks on the parts that we have. So if we connect across the two ends of our wrist strap with our multimeter, and I have my multimeter set to ohms, so there's one end connected to the banana jack, slight tripod adjustment, and now I'm going to connect, I'm going to zoom in just a bit. There's one end connected to the banana jack, and now the other end connected to the snap. And these purposefully have a 1 mega ohm resistor in them to keep you safe if there's anything wrong with your ground, if it accidentally gets shorted to power. So as you can see there, we're reading 0.98 mega ohms, or about 1 mega ohm. So our wrist strap has this safety resistor in it, just as it should. Similarly, we can take a look at our ground strap, or our ground cord rather. So of course we have our two ends, the end that we're going to ground and then the end that goes into the snaps on the mat. Most mats have snaps on two corners. There's one on one corner, there's one on the other corner. We'll insert that once our ground is good. But first let's examine the cord. So I'm going to put one end of my multimeter, still set to ohms, around the ground loop. And the other end I'm going to touch to either of the banana jacks of the snap. And we should get essentially continuity there because we're going directly across the wire. And sure enough, there we have 0.2 ohms, 0.3 ohms. And bear in mind the leads of the multimeter are probably about that much. So essentially we have perfect continuity there. Now, for safety reasons, if we go to the snap, just as with the wrist strap cord, to insulate us and keep us safe, we're going to have a 1 mega ohm resistor placed from there to there. So when we go directly to the snap, we're going to see about 1 mega ohm of resistance, and there we are, 1.05 mega ohms. So these cords are working as they should be. So now the next step is for us to ground this loop end. So now we're ready to consider the first of our two options for grounding the loop end of our ground cord, and that's going to be with our wall outlet. Now before I get started here, I'm going to offer some words of caution. How I'm going to show you how to do this is how I've done it, and I've had my mat connected this way for quite some time and I haven't had any problems at all. However, realize that faults do occur in wiring, and no matter how cautious you are, there's no absolute guarantees, so you are proceeding at your own risk. If you're not comfortable working with mains wiring, if 120 volts alternating current is something you've never checked before, you probably should not continue. Also, I strongly recommend using only a quality multimeter to probe mains. When you probe mains with a multimeter, you are trusting your life to that meter. Use a quality meter for this procedure going forward only. Okay, so the first thing we're going to want to do is turn our meter on to volts alternating current, And there we are. And now we're going to want to use our multimeter to check the outlet. So first let's check between line that is power and neutral for both outlets. We should get 120 volts alternating current. Again, if you live in a different country, your voltages may be different. In fact, the outlets might be different altogether. So you'll definitely have to look up the specs for your country if you're outside the United States. There we go. So 118.8 volts alternating current, I'd say that's good. Now let's check the top outlet. And there we go, finally, 118.5 volts alternating current. So that's good. Now the next thing we're going to want to do is we're going to want to check from power to ground. Again, for both outlets. And again, we should get right about 120 volts alternating current. And there we are, 118.5 volts alternating current. Now we'll do the top outlet. And once again, 118.5 volts alternating current. I lost my connection there for a moment. Yeah, there we are, 118. Lost it again. 118.6 volts alternating current. That's good. Now what we're going to want to do is we're going to want to check from neutral to ground. And there should be an ever so slight voltage, but not really a significant one. And let's see if I can get my meter in there well enough. And there we are. I'm reading less than a volt. That's about 100 millivolts AC. So I'm going to say that's good. So there's a tiny little bit of volts alternating current there, but it's less than 1 volt alternating current. That's what it should be. Now let's check the top outlet. And my connection's not the greatest there, but eventually should get about the same here. It might be a little higher. There we are. So we're about, well, slightly higher here, but still well under 1 volt alternating current. So that's good. Now here, the last step is the most important. Since we're using the outlet as a ground, it's standard that the center screw has continuity with both ground terminals. In fact, that's why these grounds are made that way. The loop is meant to have the ground screw go through it. So we definitely want to check continuity, well, I shouldn't say continuity, we want to check volts alternating current from here and here and here. All three of those should have essentially absolutely no voltage across them, because there should be a direct connection. So now I'm going to check between the ground of the top outlet and the center screw. And if we have some patience and we wait for our reading to come down and we make sure our connection is really on there well, we should get almost nothing here. And there we are, less than 3 millivolts AC, less than 2 millivolts AC. If we're patient for a little bit more, we should get under 1 millivolt AC. There we are, 0.9 millivolts AC. That's almost nothing. That's good. Now let's do the same check from the bottom outlet's ground to the ground screw. And there we go. Getting there, 2 millivolts AC. And 1 millivolt AC, less than 1 millivolt AC. I'd say that's good. And now let's check that the ground of the two outlets should do exactly the same thing. And there we are, we're getting darn close to 1 millivolt AC. 1.3, 1.2, 1.1, 1.0, and there we are, less than 1 millivolt AC. So I'm going to say at this point, we've done sufficient checks with our multimeter to say that this outlet is good. So there's one more thing that we're going to want to do, and that is we're going to want to use an outlet tester to check our outlet also. And how these outlet testers work, and you can buy these at any hardware store for $5-10, is that they have a series of codes on this label here that, depending on how these lights light up, it tells you the condition of the outlet. Now, these outlet testers are not an absolute test, but they're pretty darn accurate. If the outlet tester says the outlet's good, 99% likely it is. This particular outlet tester, if these two lights come on and this one does not, the outlet's good. So all the tests we just did previously would be a little bit much to do before every ESD session, but at a minimum we can quickly and easily take our outlet tester and check our outlet. So there's our two lights on, that's good. And there's our other two lights on, so that's good. So at this point, I would say we've convinced ourselves that our outlet is good. So now it's time to remove the plate and put the ground screw through our loop. And there we go. There's our ground complete. Okay, so now let's consider the second of our two options for how we can ground the ground loop of our ground cord. What the camera's pointed towards here is I pulled the access panel in one of the walls of my bedroom that leads to the pipes for the shower. And I'll try and get a shot of it directly. I live in a basement floor apartment, but for example, this pipe I can see goes directly into the ground. And if I kind of tap on it, it's very clearly not a plastic pipe. That's a good old metal pipe. So that's going to work for us. So to attach our loop to this pipe, we can buy special made connectors just for that purpose, or if you want to do it the convenient way, you can buy just a regular old worm drive hose clamp that you can buy at any auto parts store or hardware store that you turn with a regular old flat blade screwdriver. These will cost you maybe $1. So let's go ahead and attach that to our pipe that we see is going nicely into the ground. Okay, one final tighten, and there we go, just nice and snug. That'll do it. So now we have our ground cable nicely attached to a ground. So the next thing we're going to want to do is we're going to want to check and make sure that that ground is as good as we think it is. Okay, so now that we've physically made our connection between the loop end of our ground cord and what we believe to be metal physically going into the ground, the next thing we want to do is check that connection. Now in the case of the previous shot, for me living in a basement floor apartment, it was definitely very clear that that was a metal pipe and that it was physically going into the ground. But if you're doing this on, say, the first floor or the second floor of a house or apartment, or if you own a newer house and you have plastic pipes, say, or you're connecting something to a radiator and you're really not all that sure that that radiator is definitely going into the ground, you definitely want to verify that that ground that seemed to be good is in fact good. So the next step that we're going to do is what I showed previously, where you verify that the ground of one of your mains outlets is good. Then we're going to want to connect one lead of our meter to that known good outlet ground. And then we're going to want to, for the moment, leave the other lead disconnected and observe the voltage that we see. And you'll notice two things about the voltage. For one thing, it's significant. It's currently about 330 millivolts AC. And the second thing we'll notice is that it's fluctuating quite a bit. That's what we would expect, since this probe is not touching anything. Now we want to next take the probe that wasn't touching anything and connect it to the banana jack end, or banana jack opening rather, of this end of the ground cord, that is where the other end of course is connected to our metal pipe. And what we should see is that voltage that's now both significant and fluctuating should stabilize, decrease dramatically. And that's going to tell us that the ground that this is connected to is just as good as the mains ground that we verified. And there we go. The voltage dropped from anywhere it was fluctuating from like 300 to 500 millivolts AC, and it pretty much instantly dropped to a dead, solid, steady 19.3 millivolts AC. So this ground we know now is as good as the mains ground that we verified earlier. So that's definitely all set. Now we just have to make the final connections to our mat. So here we are back at our ESD mat, and using one of the two methods we've just seen, we've successfully grounded the loop end, the other end of this ground cord. So now we can attach this end to the snap on the mat, and now our mat's grounded. And then we're going to want to take the banana jack end of the wrist strap cord, plug it in, and then connect the other end of the wrist strap cord to our wrist strap. And now, as soon as we put our wrist strap on, our entire body's grounded. So now we can reach for our static sensitive 18F4550s, take them out of their ESD bag, pop off this retainer here, and slide out our 18F4550s and be confident that since we're still grounded, we're not doing any ESD damage to these chips at all. So our ESD station is all set up and good to go.